Welcome to Demystifying Math. In this lesson, we're going to be discussing the normal curve. A normal curve is drawn. The area between the curve and the horizontal axis is 1, or you could think of it as 100% of the area. The normal curve will be representing a set of data values, where it is normally distributed with a mean of 0 and a standard deviation of 1. For a normally distributed set of data, the mean, the mode, and the median are all equal. On the graph, they're located at 0. The curve is symmetrical about the vertical line at 0, which means that 50% of the area under the curve is to the left of the mean and 50% of it is to the right. Or you can think about it as 50% of your data values will be below the mean and 50% of your data will be above the mean. Remember, the mean and the median will be the same for normally distributed data. Approximately 68% of the area under the curve is within 1 standard deviation of the mean. That means that we have 34% of our data values between the mean and 1 standard deviation. Approximately 95% of the area under the curve is within 2 standard deviations of the mean. Again, you can break that up, so you have 47.5% of your data values between the mean and 2 standard deviations. Approximately 99.7% of the area under the curve is within 3 standard deviations of the mean. It is very unusual to find a data value that is beyond 3 standard deviations from the mean. Again, you can split that up, so you have 49.85% of your data between the mean and 3 standard deviations. A z-score will tell us how many standard deviations a data value is from the mean. To find a z-score, we will take the data value minus the mean and divide by the standard deviation. Let's look at an example. Suppose that you have a set of test scores that has a mean of 75 and a standard deviation of 2. Let's find the z-score for a test grade of 78%. So our data value is 78, our mean is 75, and our standard deviation is 2. So we get 1.5 as our z-score. So on our normal curve, a 1.5 z-score is between 1 and 2. Now we've shaded the area to the left of 1.5, which means that we're looking for the number of test scores that are below 78%, or expected to be below 78%. Since this is not one of our standard areas, we're going to go to our graphing calculator to find the area below 1.5 as a z-score. So to find this area, we're going to go to distributions, which is second variables. So look for your variables key if you're using a TI-84 or 83. And go second variables, and then choose normal CDF. This will be for our normal distribution. And we want to start at negative infinity. So negative infinity to the graphing calculator is something like negative 10,000. And then we want our upper limit to be our z-score, which is 1.5. Since we're using a z-score with a mean of 0 and a standard deviation of 1, we'll just leave that the same. And then hit enter twice. And that gives us an area of 0.9332 approximately. So we're going to use that. So that tells us about 93.32% of the scores are expected to be below 78%. Now we could also find what percent are expected to be above 78%. So it kind of makes reasonable sense that we would just do 1 minus because the area under the curve is 1. So 1 minus the 0.9332 gives us 0.0668, or 6.68% of the students will score above 78%, which is kind of reasonable since 93% are scoring below. Let's look at another example. Suppose that a dishwasher has an expected lifespan of 9 years with a standard deviation of 1.6 years. What percent of dishwashers are expected to last longer than 10 years? So we're going to again start by finding our z-score. So our data value is 10 years and our mean is 9 years and our standard deviation 1.6. That gives us 0.625 as our z-score. So we're going to plot that on our curve. And what we want to do is shade the area to the right of that because we want the number that are going to last longer than 10 years. So we're going to go back to our graphing calculator and figure out what area that is. Okay, so we're going to go back to normal CDF. So that was second, variables, choose number 2. Now this time we want to start at 0.625 as our z-score, and we want to go to positive infinity, which will be positive 10,000. Again, our mean is 0 and our standard deviation is 1, and we're just going to hit enter twice. So that gives us area of 0.26598 or 0.2660. So let's go ahead and use that. So that tells us that 26.6% of the dishwashers are expected to last longer than 10 years. Now, again, we can do less than 10 years. So that would be the area to the left of 0.625, which will be 1 minus the area to the right. So that gives us 73.4% of the dishwashers that are expected to last less than 10 years. What is the probability that a dishwasher lasts 10 years? Exactly. Well, we can't do exactly, but we can do between 9.5 and 10.5 years, and that'll give us anywhere within that 10-year range. So we're going to find 2 z-scores this time. First for the 9.5. So we have 9.5 minus 9 over 1.6, which gives us 0.3125. And we're going to also do it for 10.5. So we got 0.9375. So we're going to find the area between these two z-scores. So it looks something like this on our graph. So let's go back to our graphing calculator and do that. So we're going to use the normal CDF this time. So second, variables, number 2. And this time we have 2 endpoints. So we want to do 0.3125 and 0.9375. And our mean is 0, our standard deviation is 1, and I'm just going to hit enter twice. So we have 0.2031 approximately as our area. So about 20.31% of the dishwashers are expected to last between 9.5 and 10.5 years, or approximately 10 years exactly, or anywhere within that 10-year range. Okay, thank you for watching.